Maybe today I will cover the tutorial.
Okay. So
Yeah, today I'll cover, yes.
But
Then
after lunch, you will have break?
I'll have
Shruti
break. Yeah, she will cover. Yeah.
And tutorial, I think I'll come back. And actually, I have a class from 3 to 4. So if you don't mind, I
Okay.
can take my class.
Yeah.
From 3
Okay.
to 4.
Yeah.
I'll be
Okay.
back here at 4.
Yeah.
Yeah.
Anyway, we are slowly drifting.
Okay.
So I think 4 o'clock I will start my tutorial.
So then I'll come, sir.
Because we are slowly. I mean, there is a delay, right?
Delay. So we will come. I'll join this. Around 2:15, 2:30 I will leave. 3 to 4 I have a class.
Okay.
So I will join in
okay.
your tutorial.
Yeah. Okay. Okay. Sure.
I will also. I'll come back. I have some.
Yeah. Okay. Okay. Sure. Yes. Okay, so before we move on to learn about the physics, material science aspect of magnetic recording, it's good to have some background information. So how we make hard disk drives, how things work, like what are the technologies, sputtering, some fundamentals are required. So we'll go through those slides for the next few minutes. But before that, I want you to watch this video. Do you get the audio here? Will you get the audio here?
Every Seagate drive is comprised of sophisticated components, recording heads, recording media, electronics, and firmware, all playing a critical role in the storage of information. We have hundreds of scientists and experts in everything from chemistry, physics, and process technology to fluid mechanics and aerodynamics. These specialists design and build the world's most advanced digital storage products by combining their collective expertise. All of the information stored on a hard drive travels through the recording head. This tiny electromagnetic wonder hovers less than 100 atoms above the disk, a gap 100 times thinner than a sheet of paper, reading and writing information on a surface spinning up to 15,000 revolutions per minute. To build these advanced recording heads, silicon wafers are sectioned into increasingly microscopic pieces, attached to mechanical arms called suspension assemblies. These heads are so small that Seagate's thousands of square feet of clean rooms need to be 100 times cleaner than a hospital operating room. Seagate engineers put these recording heads through rigorous testing, screening, and precision measurement before they are positioned in a hard drive. Recording media are the spinning disks that store the information on a hard drive. These disks are manufactured starting with substrates, typically made of glass or aluminum. Then, microscopically thin layers of highly specialized magnetic films are applied, enabling the storage of all those trillions of zeros and ones that make up the digital content. The disks are also polished and lubricated before a multi-disc writer applies servo patterns onto each media surface. These servo patterns create a map that determines where all the digital data can be located. The disks are now ready to be integrated into the hard. This is where Seagate engineers bring together all of the heads and disks, integrated circuits and motors, software and firmware, and other critical technologies. Assembly begins with base decks, including the motors that spin the disks. Each deck has an electronic tag, similar to a digital fingerprint, that tracks the drive from assembly to testing and also stores key information. Precise and fully automated machinery combines the sophisticated components for each drive. Parts are assembled, balanced, measured, and adjusted according to demanding tolerances. Then, in their state-of-the-art automated testing systems, Seagate can analyze more than 1.5 million drives at a time. These drives will undergo thousands of tests to make absolutely sure they meet our customers' exacting criteria. Our drives are put through procedures that push them beyond reasonable limits in all phases of a drive's development to make sure they run smoothly in all kinds of systems and demanding environments. From an acoustic vault to help us eliminate noise, to chambers that simulate altitudes up to 40,000 feet and pressures well below sea level, drives are cooked to extreme temperatures. We shape and drop them, and hit them with thousands of power on and off cycles. Seagate scientists keep dreaming up new ways to test the limits, all with the goal of making sure those drives perform as promised. Seagate is leveraging more than 30 years of leadership in hard drives to develop the next generation of storage technologies. Solid-state drives and hybrid combinations of solid-state and traditional disk storage are already being delivered to customers worldwide. And we continue to push the limits of rotating hard drives with discoveries such as heat-assisted magnetic recording. The future demands increased capacity and faster performance, and this is just the beginning of what's going on in our R&D labs to meet the world's insatiable need for digital storage. Over the next year alone, people in their computers will generate 40 exabytes of new information, the equivalent of 700 billion hours of music, or 13 trillion digital photos. That's a lot of hard drives needed. Hundreds of millions of them. Seagate meets this unprecedented demand through customer-focused innovation and operational excellence. Building 6 hard drives, hybrid drives, and solid-state drives every second. And every one of those drives journeys through more than 1,000 manufacturing steps, flawlessly calibrated to provide the most reliable and consistent supply chain for the more than 1 billion devices delivered to our customers worldwide. Seagate is building the performance, reliability, and quality you depend upon, so you can store, share, protect, and enjoy your digital life.
Okay, so you saw how advanced is the manufacturing technology, right? So how many people did you see? How many humans did you see in the video? Almost no, right? So all these technologies are so precious. We don't want humans in the hard disk technology. Okay, one reason is, so I told you that there is something called head that reads and writes information in hard disk drive. So, do you know what is the spacing between the head and the disk? Yeah, so it's, they said 100 atoms. So 100 atoms is a bit too long. I mean, that may be very old technology. So let's say 1 atom is how big? Huh? Angstrom? 1 angstrom. Okay. So 100 angstrom is 10 nanometer. Okay, this is very old technology. Okay, 10 nanometer is very old technology. In current hard disk technology, the spacing is 1 nanometer. The spacing between the head and the disk is just 1 nanometer. So if you take a dust particle, is several micrometer. Okay, so you don't want any dust particle to go onto the surface of the disk. Okay, so if there is a dust particle, then you fly your head at 1 nanometer spacing, is going to crush. Okay, so we don't want to have that problem. So most of the hard disk manufacturing is automated, and when you make the disk, you have to make it very smooth. So with a roughness of the order of 0.2 or 0.15 nanometer. So you want to make very clean substrate, very smooth substrate with no particle, all those things are happening. So we don't want humans inside the hard disk manufacturing. Okay, so in this part of the lecture, let's go into some of the details. Okay, you don't need to remember all this information, so I am just giving you some idea of the processes that are involved in making a recording medium, the disk. Okay, so the video you saw talked about various things, right? Disk, then head, how the hard disk is assembled, and so on. But here I am just showing some of the processes used in the recording medium, the disk itself. Okay. So first part is the substrate shaping. You want round disk, right? Circular disk with a hole. So the final disk has to look something like this. But for that they may start with a plate, then cut the disk into this. Okay. Then they will shape it. Okay, they will do some shaping. So if you look at this edge, it has to be like this. So there are specifications of how much this should be, how much this should be, and so on. Okay. So if I zoom in this part, it will look something like this. So there are specifications. So all these specifications are met during this stage. So that's called substrate spacing, shaping. Okay, then I told you that the roughness is 0.2 nanometer or smaller. So you have to polish the substrate. Okay, when I say substrate, basically this is something that holds the information. The substrate holds the thin films. Okay, we will be using thin film for storing information. Basically, the substrate is the one that makes the disk hard. Okay, so you have a hard disk because of the nature of the substrate. So that holds the substrate. That holds the thin film. And anyway, we will learn about the substrate in the next few slides. So we need to clean the substrate. Then we will do sputter deposition. Again, we will learn this. So we will use this technique to make the thin films. Then we will clean the deposited disk. Then we will do something called lubrication, buffing. These are some processes. Anyway, we will cover in the next few minutes. Then finally, after buffing, the hard disk company will send it to the customer. Okay. So this is roughly the process involved in making a recording medium itself. Okay. So now let's go into the detail. So as I told you, substrate is a piece of material that holds the layers on the top. Because you will learn that the thin films that store the information in hard disk drive, they are all nanometer scale. Okay, 1 nanometer, 2 nanometer, some may be 10 nanometer. So those films cannot stand on themselves. Okay, you cannot use the films as such. So you have to deposit on something very solid. So the solid piece of material that holds all the thin film is called substrate. So in hard disk technology, there are two types of substrate traditionally. One is aluminum alloy. So I told you that they will take a piece of material like this. So this may be aluminum magnesium alloy. So they will have a sheet, then they will cut into this shape, then they will bring it to this shape. Okay. So aluminum magnesium alloy is cheaper, so that's one advantage. And this is a light metal, so it's easier to polish. So if you want to make smooth surface, it's easier to polish. But aluminum alloy has certain inferior mechanical properties compared to glass. So for example, if you have a disk and if you rotate at very high speed, there may be nanometer scale fluctuations. Okay, so we are flying at a spacing of 1 nanometer. Okay, so if there are some nanometer level fluctuations, then the head and the disk may crash. Okay, which we don't want. So this is one of the drawbacks of the aluminum magnesium based substrate. Okay, I'll play a video to illustrate my point. Okay, so I don't know how many of you have seen these guys' video. They create videos at with a high speed camera. So in this case, they rotate CD, the compact disc, at high speed and observes what happens. Okay, so let's watch.
Let's blow it. That's ridiculous. We shot 96 gigs. In Oh, look at that. That's awesome. Just the shape it makes when it shatters. It's like a little tree.
So CD is a plastic disc. So when you rotate at very high speed, it's not flat anymore. So there are some oscillations. So there are some oscillation, and when they oscillate, they hit some bottom of the motor and they break. Okay. So similar thing we don't want to happen in our disc, because we are flying at 1 nanometer. Here the spacing may be a few millimeter and the oscillations break the CD, but here we don't have much spacing. We have only 1 nanometer spacing, so we don't want to have the oscillations. So that's one of the drawbacks of aluminum. So usually the aluminum alloy substrates are used in desktop. So if you have a desktop you don't move often, then we can make aluminum alloy based hard disk drive. So if you have a server which you don't carry around, then aluminum alloy is good. Okay. On the other hand, if you want to have hard disk drive for your laptop, then people use the glass substrates. So glass substrates have better mechanical properties. That means they don't have the waviness, so they are very rigid. So when you rotate at high speed, they don't have the mechanical waviness, so they don't break easily like this CD. So that is the advantage of the glass. But the problem with the glass is it is expensive to manufacture and they are difficult to polish. Okay, so to give you some anecdotes, right? So when I was in my previous organization, one company which specializes in glass, they came to my organization. Then they were looking at whether they can make glass substrates for hard disk industry. Then we told them that this glass has to be like 0.2 nanometer kind of roughness, very smooth, and it has to have this kind of mechanical properties and so on. Then they realized that it's not a good proposition for them to come into this industry. Okay, they are very good in glass. They make plates and sell plates. Okay, so if you buy their plates, it may be like $10 or $15. But if they make this kind of substrate, it is only like selling for $5. Okay, so it's a lot of difficult requirements, but it is very cheap. So that's why they didn't join. They didn't venture into making glass substrate. They just quit that idea. So what I'm saying is that the substrates have to be very smooth and very rigid, so that you can have the thin films deposited on the hard disk drive, so that the head can fly at 1 nanometer spacing. So typically there are two sizes, as I mentioned. So 65 millimeter, 95 millimeter are the standard diameters, and as I told you before, recently the hard disk is also going to 97 millimeter diameter. Okay, so we already saw this one. So the next step, you have made the substrate. Now you have to deposit the layers. The information that we store in hard disk drives are stored in several layers that we make on top of the hard disk drive. So for this purpose, we employ a technique called sputtering. Okay, so how many of you have heard this term, sputtering? Okay, so many of you are aware, some of you are not aware. So I'll go through the explanation. So in simple terms, we can explain sputtering as playing billiards with atoms. Okay, so you play billiards with atoms, then you can deposit thin films of material. Okay, so I'll go through the sputtering by showing a video. Okay, so in this case, you have something called target. So target is a piece of material which provides the atoms. For example, let's say I have a substrate, and I want to coat this substrate with a tantalum film. Okay, let's say I want to deposit a piece of a thin film of tantalum on the substrate. Then my target will be tantalum. So I have a tantalum target. So what I am going to do is I am going to play billiards with this tantalum target. So I am going to send something that will knock this tantalum. Then the tantalum atoms will go everywhere, and they will also get deposited onto the substrate. Okay, that's what is going to happen. So here I have a target and I have a chamber here. Okay, so the chamber has argon gas. So because we apply some voltage, the argon gets ionized. So these red are argon atoms. So these argon atoms are accelerated towards this target. You see, target is at a negative voltage. So target is a cathode. So it will attract argon ions. So argon ions will knock these tantalum atoms. Tantalum atoms will go everywhere, and they will also get deposited onto the substrate. So this is called a sputtering process. So I'll repeat again. So I send argon gas. Argon gas gets ionized. After electrons go out, you have argon ions. These are positive. This is a negative voltage. So negative voltage will attract positive ions. So they come with some energy. So they knock off atoms. These atoms, blue atoms, go everywhere, and they will also get deposited onto the substrate. Okay. So this is called a sputtering process. So it's a physical deposition. So you transfer momentum from the argon ions. So it's basically transfer of momentum that releases atoms from a particular surface, and these atoms get deposited onto the substrate. So this is called DC sputtering, because we are applying a negative voltage to the target. So this is cathode. Then the rest of the system is grounded. So with respect to the rest of the system, which is at 0 volt, this is at negative volt. So this is called DC sputtering, direct current sputtering. Okay, so this is a simple view of a sputtering chamber. So you have a chamber, and inside you have some target, and here you have substrate, and this chamber you pump using some vacuum pump. So sputtering is typically carried out in 10 power minus 7 torr or even lower pressure. So we evacuate the chamber for a low pressure. Then we send inert gas to the chamber, and we apply large negative voltage to the target. So during this process, target attracts argon ions, so they knock the target atoms and they get deposited onto the substrate. Okay. So I'll play another video to describe the whole process. Okay, so in this animation, now this is the chamber. Inside we are going to do sputtering. Okay, so inside the chamber you have the target here, substrate here. Initially the system has a lot of gas molecules. So you don't want these gas molecules. So what you do, you switch on the vacuum pump and suck all the molecules out. So you create as low pressure as possible. So after you create a low pressure, then you send argon gas shown by the blue color. Okay. So now you created low pressure, send argon gas inside the chamber. Okay, so this argon gas pump will be on, argon gas also is flowing at the same time. Okay, so this keeps happening. Now you apply a negative voltage to the target. So there is something called plasma happening. So plasma is the fourth state of matter, which means there is an equal number of positive and negative ions, and as a net it has no charge. Okay. So when the plasma is formed, the argon ions will knock the target, and the target atoms will go and get deposited onto the substrate. Okay. So this is the sputtering process. Any doubts so far? Okay, so DC sputtering as such is not good. Okay, so people add a modification to the DC sputtering. So the modification is called a magnetron sputtering. Okay, so as the name implies, the magnetron involves some magnets. Okay, so what happens is that if you just use DC for sputtering, we need very high voltage, and that's not very good. So people add a set of magnets below the target. Okay, so these magnets will produce magnetic flux. When there is a magnetic flux, there will be Lorentz force, right? So you know the electrons have charge, and you have E V cross B force. Okay, so or if you have charge Q, Q times V cross B is the Lorentz force. So this Lorentz force makes the electron to spiral around, and when electrons spiral around, they knock more argon atoms. So there are more ionization. Okay, so because there are more ionization, more argon atoms, we can sputter at low voltages. So if you need 1000 volt for DC sputtering, but if you have magnets below the target, you can sputter at much lower voltage. Okay, around 400 volt you can sputter. So this is one advantage of the DC magnetron sputtering. Secondly, you have more ionization. So when you have more ionization, the rate at which you can knock the atoms off will be higher. So you will have better deposition rate. Let's say no magnet. When you have no magnet, let's say you deposit 1 angstrom per minute with a magnet, you may be able to even deposit like 1 nanometer per minute or much larger. Okay, so the deposition rate can be increased by adding magnets below. So this is called DC magnetron sputtering. Okay, so this is based on the Lorentz force which I described before. So Lorentz force is V cross B force. Okay, so I'll play this video. Maybe for streaming it's not important. Let's just play the video.
Potential on this electrode so high that it actually boils the electrons come off the electrode, makes just a beam of electrons. It also has some a little bit of background gas that ionizes to keep everything stable and doesn't charge up too much. But mostly you have electrons flying off this electrode, and most of them go straight to this metal plate, and that's the end of the story. But there's a little slit in the plate, so some of them get through and make a beam that keeps going. So you've got a beam of electrons, and this little plate is tilted a little bit, so they slowly, along this direction, they crash into the plate. The plate has a phosphor on it, so it lights up when they crash into the plate. So when I turn it on, there you can see the beam. That's a beam of electrons flying through the tube. So what we're going to do is bring a magnet and see what it does to the beam of electrons. Because remember, this bar magnet the field lines go from the north pole, the red is the north pole, to the south pole. So if we just think about the poles or the field right at the ends, because we're going to use the ends, it'll be this way near the north, and it'll be pointing in the south. So I will bring the north pole pointing at me at the beam, and let's see what that'll be. We have the beam going this way, and I'm going to bring this pointing in, so we're going to have a B field like this. So V cross B also the same as this. It should be up. Right? So let's see what happens. There's our beam, and I bring in this magnet. Oh, there's the deflection we hoped for, but it's down. And it's down. And why is it down? It's down.
So you saw the electron beam, and when he brought the magnet, you saw that there is a bending, right? So there is a V cross B force acting on the electrons. So he said the electron beam will go up, but it went down. Why? Yeah, because it's because negative charge. So he didn't consider that first, because the Q is the negative, so the direction is different. Okay. So we are using this Lorentz force to increase the deposition rate. So if it takes 1 minute to make 1 angstrom without magnets, with magnet we can increase the deposition rate. We can deposit 1 nanometer in a minute. Okay. So here I have drawn the cross section. Let's say this is the target. Let's say this is the tantalum target from which you want to deposit tantalum film. Okay. So below the target we have an array of magnets. So in the cross section you can only see 3 magnets, but if you see the top view, you will see like there is one magnet, ring magnet inside. Okay, so this is represented by this symbol here, and you see the 2 other magnets are represented by this array. Okay, so when you have one magnet, let's say this is with the north pole towards you, this is with south pole, then there will be a magnetic flux in this direction. Okay, so around those magnetic flux lines, the electrons will spiral around. So when electrons spiral around, okay, so these are the magnetic flux lines. So electrons will spiral around. So they will knock more argon atoms. So there will be more argon ions. So these argon ions will be now accelerated towards this target. So there will be more sputtering. Okay, so that is the concept of DC magnetron sputtering. So we have an array of magnet like this, and okay, this we can skip. So let's do some question. mic. Okay. So these are amorphous materials, and let's focus on crystalline materials. So most crystalline materials may be fitted into 7 crystalline systems and 14 lattice types, and the 7 crystalline types are cubic, tetragonal, okay, all these type of systems. And in this course we will deal mostly with the cubic systems and hexagonal material systems. Okay, so you don't need to remember all these different types except cubic and hexagonal. So how we define cubic or hexagonal depends on the unit cell and the lengths and the angle. Okay, so in cubic system the length A, B, C are the same. So A is equal to B is equal to C, and the angles are all 90 degree. Okay. Tetragonal, orthorhombic all have their own definition. In the hexagonal case, let's say this is the unit cell. Let's say these 4 atoms at the top and the 4 at the bottom, and this segment you take out, that is the unit cell. So there A is equal to B, but C is different. Okay, so you notice that this length and this length will be the same. So A is equal to B, but C is longer. C is along this direction. C is longer, and alpha is equal to beta is equal to 90 degree. That means the angle between this plane and the vertical is 90 degree. But this angle between, say, this line and this line, that's 120 degree. Okay, so that is the definition of a hexagonal lattice. So we will be dealing with the hexagonal lattice and cubic lattice in this lecture. And the cubic lattice itself has like simple cubic or body centered cubic, where you have one atom in the body center, or face centered cubic, where you have one atom at the faces of the cube. Okay, so we will be dealing with face centered cubic, BCC, and so on. So whenever I use the center, that's what is BCC. FCC means you have atoms at every corner so if you look at the covering this? Okay, then we will skip. Okay, so you'll learn about XRD and Miller indices later. So let's skip that part. So another technique that you can use to determine the crystallographic properties is transmission electron microscopy. So in this case, I mean, if you want to do transmission electron microscopy, you have to make a very thin samples, and the electrons will go through, and you can visualize the atoms. So if you look at this picture, so this group of scientists, they have made, they looked at the iron platinum, how they are arranged, so you can see the atoms. So transmission electron microscopy is another technique through which you can observe the patterns and so on. Okay, so there are various techniques through which you can check the crystallographic properties of materials. So I want to give you also some definition of the difference between single crystal and polycrystalline materials. So when I told you that there is a lattice, and the lattice will be like extended over large distance. So materials in which there is a long range order, they are called single crystals. Okay, so this long range order may extend over several hundreds of millimeter or even centimeter and so on. Okay, so silicon wafers used in the production of ICs are single crystals. Okay, so that's one type of crystalline material. Then another type of crystalline material is called polycrystalline material. So in polycrystalline material, you will have the atomic order over a very short range. So if you go from one region to another region, maybe there is a difference. Okay, so this is one example of a polycrystalline structure. So you can see that there is a black or gray region surrounded by white region. So within this small gray region and the black region, you will have atomic order. And if you step out, you go into the white region, there is no atomic order. So this region is amorphous. Then again you go to the next black region, there is crystallographic, I mean there is a periodic arrangement of atoms. Okay, so this kind of arrangement where there are grains. Okay, so these small regions are called grains. So within this grain, there is a periodic arrangement of atoms, and if you go out of this region, there is a grain boundary. Then you go to the next grain, then again you will have periodic arrangement, but you see that the periodic arrangement is a very short range in order. Okay, so such materials are called polycrystalline materials, and this picture roughly tells you the difference between single crystalline, polycrystalline and amorphous material. So in amorphous material, there is no order in which atoms are arranged. Single crystalline materials, you can see perfect order, and in polycrystalline materials you see one region there is order, there is another region where there is order, and so on. So we have many regions within which the atoms are arranged in certain order. So they are called polycrystalline materials. So these are the nanostructured grains that we see in hard disk drive. So this is a transmission electron microscope of a hard disk media, where we see this kind of polycrystalline material. Okay, so we call these small regions as grains. Okay, so in polycrystalline materials, you will have one grain here, another grain here, another grain here. Then there is a grain boundary, and you see that there is a order, but the order is different between grain A, B, and C, and so on. Okay, so this is the property of polycrystalline materials. So in hard disk drive, we are mostly using polycrystalline materials. Okay, so let's do some questions. Okay, we can use XRD TEM. Okay, that's all. So we ended 5 minutes earlier. Okay, so we'll go for lunch break. Thank you. Thank you.